All right, we can begin. Welcome to CS3510, L11B. The topic of today is satisfiability. So last time we talked about a gentle introduction to the notion of problems, the notion of hardness, conditional hardness, things like this. Today we're going to finish all that up and talk about one NP-complete problem. So we make this notion of a relationship among problems. For A, B problems, we say that A is polytime reducible to B if there is function f computable in polytime such that x is an element of A if and only if f of x is an element of B. Equivalently, x is not in A if and only if f of x is not an element of B. Right? This is just a formal definition. What you should think about is that we have problems here in A. There are things that are good and there are things that are bad, right? So we have something like this. A is here, and then A complement is here. These are the space of all things. These are things that are good. These are things that are bad, right? We have B here. B has its own things that are good and its own things are bad. The polytime reduction simply preserves correctness. It maps good to good and bad to bad. In that if x is in A, then f of x better be in B. And if x is not in A, then f of x better not be in B. A polytime reduction need not be surjective. It need not be injective. It need not be anything except that's it. It just needs to be computable in polytime and have this correctness property. F of the polytime reduction is the translation. It is the way you can translate hardness about one problem into another. In the sense that if there's a polytime reduction from A to B, A and B are polynomially related. They have a relationship. So it could be the case, and it will often be the case, that A and B are both very difficult to solve, exponential time, but you can translate between A and B efficiently. So that allows you to say if one is hard, then the other is hard, and if one is easy, the other is easy. We'll emphasize that soon, but this is what we're going to spend a lot of time doing, is constructing such polynomial time reductions, right? So let's prove the following. We want this to mean, let's suppose we have a reduction from A to B, okay? And the way to think about this is if B is easy, that implies that A is easy, right? Equivalently, if A is hard, then B should be hard. In the sense that B is over there, it's rightward of A, right? We're comparing problems. They're not like numbers or anything, but that's what this relation is defined upon it, when there exists a computable function that translates from A to B, right? So B is harder than A, and E is easier than B. That's kind of what we mean, right? So we can prove and by hardness, we don't mean like n squared, n cubed. We mean up to a polynomial. Again, great use of definition of P. So we prove the following. If there's a polytime reduction from A to B, and B is an element of P, that implies that A is an element of B. So this is the proof that if B is easy, then A is easy, as long as there's such a translation between A and B. Before we prove this, any questions on this? Since there's a polytime reduction from A to B, there is a function f such that x is in A if and only if f of x is in B, and f of x computable in polytime. Right? Let B be in P. Then there is polytime algorithm. We'll call it alg for B. We give a polytime algorithm for A. It's going to look like this. Alg for A on input x. It's going to compute f of x. And then it's going to return alg for B on in f of x. What is the runtime of this algorithm for A? What is it at least dependent upon? Yeah. How long does it take to compute f of x? That takes polynomial time. How long does it take to run the algorithm for B? Polytime plus polytime is polytime. So this is a polynomial time algorithm. So that's enough for us to say that A is in P. Let us illustrate this a bit more. We want to determine if some problem is here or here. Can you distinguish between the good and the bad in polynomial time in A? What we do is we translate in polynomial time, and then over here we can distinguish in polynomial time. So if this was false, we knew it had to come from here, and if it was true, we knew it had to come from here by the correctness of the reduction. So the reduction simply translates for us efficiently, and then if we can decide on the right efficiently, then we can decide on the left efficiently by the translation. That's all this really says, right? So if B is easy, then A is easy. That's what we just proved. If you have a polytime reduction and a polytime algorithm, combine those, you now have a new polytime algorithm. So if B is easy, then A is easy. Now, rather than care about that too much, we actually care about its contrapositive. What is the contrapositive of this? $20.50 question.
A is hard as B is hard.
Yes, formally.
It's not in P.
Yeah. So this also proves that if A is not in P, that implies that B is not in P. So if A is hard, B is hard, right? Otherwise, if B was easy, then A would be easy, right? This is our core relationship. If we do a reduction from a known hard problem, and we reduce from a hard problem to an unknown problem, that new unknown problem is hard. That's how we can convince ourselves the problem is hard. We have some known set of hard problems. We say, well, we can reduce from a known problem to an unknown problem. That will imply that the unknown problem is now hard. It's elevated to the special class. That's what the polytime reduction tells us, right? It has some important properties. Suppose we have a polytime reduction from A to B and from B to C. If we can reduce from A to B and B to C, what do we know should be true? Yes. And does anyone know the name of this property? It's transitivity. Yeah, it's transitive. What's the proof? Yeah?
In this case, we can just say f from A to C is just the composition of f from A to B and then f from B to C.
Okay, suppose we go f from A to B. And let's suppose we go, I don't know, g from A to C, B to C, excuse me. You can compose those two, and you'll get a function from A to C. Importantly, you'll also get a function that's computable in polynomial time. The reduction from A to C is simply run f, then run g. That's the runtime of f plus the runtime of g, which is polynomial plus polynomial is polynomial. So in fact, you can have, this is important, polynomial time reduction is transitive. So you don't have to repeatedly do some reductions, you can in fact do simpler reductions, as we'll see. Okay? So here's how you prove a problem is NP-complete. B is NP-complete if two things must be proven. One, B is an NP. The notion of completeness means that it's hard, but it's the hardest problems in NP, but they're still in NP. So not only is B in NP, but it's the hardest problems in NP. But it's not out of NP, right? So two things must be shown. One is that B is in NP, right? So if I were to plot this, this is P, let's say, and let's say this is NP. Okay? By proving that B is in NP, we prove that it's at least verifiable. There are things that are way out of here, stratospheric. There are known problems that are not in NP that go way over here somewhere. But by proving it's an NP, you're at least proving that it's easy to verify. It could be the case that it's in P, but you're also certain that it's not harder than NP, in the sense that you can at least verify it efficiently. The second thing you need for a problem to be NP-complete is that for all A in NP, there's a polynomial time reduction from A to B, in the sense that for every problem that's in NP, there is a reduction from A to B. So it's harder than all of NP, yet still in NP. So what we say is, it looks like this. This is what we would call NP hard. And a problem is NP complete if it's in NP and NP hard. The second property is just called NP hard. The problem is NP hard if it's harder than NP, in the sense that there's a reduction from everything in NP to it, right? But you can overlap with NP just a tiny bit here, right? That is where NP-complete problems go. If a problem is NP hard, it's over here somewhere. Every problem in NP reduces to it. So it's something harder than NP, but it's not too hard because you can still verify it. That's what we mean by when we say a problem is NP-complete. It's the hardest problems that are in NP. You can construct problems that are harder than NP, and you can construct problems that are in NP, but not the hardest problems in NP. Everything in P, in fact, satisfies that definition. But by having both these properties, you ensure it goes in this little special area, which is the tip of NP, the hardest part of NP. It's still in NP. It's easy enough to verify, but it's harder than all of NP. That is what we mean by NP-complete. It is a single problem, in fact, that represents an entire class of problems. Are there any questions on the definition of NP-completeness? So far, none? Okay. We need to talk about certain problems, so let's just introduce one. The canonical NP-complete problem, which is what we'll talk about today, is called SAT. And it comes from logic. So we say that a variable may assign itself a Boolean value, and it's of the form x, y, z, something like this, right? A literal is of the form a variable or its negation. A clause is an or of literals. For example, x or negation of y, or z, or negation of x. Something like this, right? And we say a formula is a CNF if it is an and of clauses. Something like this, right? So this is what the definition of a CNF is. Anyone know what CNF stands for? No. Actually, yes, a different class. Chomsky normal form, not here. It's conjunctive normal form. It's conjunctive because it's an and of ors. The ands go on the inside. In each one goes the ors. Now, this is what the problem of SAT is. This is what inputs to SAT look like. They're logical formula. And I'll just tell you that we define the problem of SAT to be such logical formula encoded in some way such that phi has a satisfying assignment. A satisfying assignment is that you can take all of its variables, plug in 1 or 0, compute the ands and ors, flesh everything out, and then you will get a 1. If there is a way to plug in 1s and 0s, that you will get that the formula can be output a 1, then we say the formula is satisfiable, right? CNF is really, it's highly universal in the sense that many problems look like CNF. So it's a good candidate problem for this. It is the case that a lot of problems have requirements in which all of them must be met, but then each requirement could be met in several distinct ways. For example, each clause could correspond, let's say, to a law, but then to be in compliance with the law, there are a few ways to do so. Right? You may satisfy certain criterion. You may do each one in some different ways, but you must satisfy all of them in some way. Right? Satisfying one with one way may prevent you from satisfying another in some other way. Right? I'm going to give you a CNF, and I want you to tell me what inputs to it are correct. Let's see. Suppose we have a CNF of two n variables, x1 to xn, y1 to yn. And it's going to be x1 or not y1. I'll do the bar, fine. And x1 not or y1. And xn or yn. And xn not or yn. Right? Let's suppose we have a formula in CNF in such a way. What inputs satisfy the CNF?
All of them are true.
All of them are true. That is correct. If all of them are true, then it's trivially satisfied. Yeah. Are there others? Characterize all of them.
Oh, everything works.
No. There's some input that should not satisfy this, at least. First off, do all zeros satisfy this?
Yes.
Okay, so there's two inputs that satisfy it.
Each corresponding x and y have to be the same.
Why?
Because otherwise the two clauses don't hold up.
Here's an argument we can make. If this is a 0, then this must be a 1, so y must be 0. Okay, fine. If this is a 1, then this is a 0, so this must be a 1. So y must be 1, right? So this just basically checks, this is a CNF for equality of strings. You can write such a CNF for basically anything. You can encode all kinds of complicated problems. This is one for string equality. You could do perhaps a bitwise equality of something. You could do all kinds of complicated things can be encoded as CNFs, right? I claim that SAT is NP-complete. Now, there's two parts to show a problem is NP-complete, right? We need to show it's an NP, and then we need to show it's NP-hard. Let's come back to the NP-hard problem in a second. Why is it the case that SAT is an NP?
If
Sure.
you're given a configuration, you can check it.
Check what? What is the configuration?
If you're given like truth values for every variable.
So let's say let V on input, let our problem be a formula, and what's our certificate? Yeah, so let's call it C1 to Cn. What are we gonna do?
Check if it returns a true or a false.
Plug and chug. So we return Cn. Just plug the assignment and see if it works. If a CNF is satisfying, someone can easily convince you of this by just telling you what bits to plug in. That is a satisfying assignment. Okay, done. So how long would that take? That's a complicated question. It's a data structure dependent question. It's ugly. One of those things we get to be lazy about, because how is the CNF encoded? It's like, what is it? Is it parsed for you? Is it just a string? It doesn't really matter, because there's like polynomial, doesn't matter. We can just say polynomial. Now other people may care about that who teach this. I don't really, it's fine. It's okay. Suppose it's a string, and then suppose you can and or not and do that in like linear-ish time. Plugging in probably takes linear time. I get to be vague. It's okay, right? We're fine. Okay, next question. So SAT is an NP. We'll come back to the problem is SAT is NP hard. By the way, let's give two intuition. Is SAT an element of P? We can't prove this. You could prove this, you win $1 million. So I'm not asking you to prove this, but I'm asking like, why shouldn't SAT be NP? Yeah.
For each variable n, you have 2 to the n possible, right?
Exactly, yeah. So like the first solution is the naive one. There are 2 to the n assignments. Check all of them. And again, n here is parameterized to be the number of variables, right? So given n variables, there are 2 to the n possible assignments, right? So you plug and chug. And you can't, I mean, you can't do any, I don't know, you can't do it any faster than that, but you probably, we can assume you can't do it any faster than that. So SAT is probably not NP, right? What about SAT complement? Is the opposite of SAT in NP? Can you verify the complement of SAT? What does that mean? When we say a problem is, what are we talking about when we say that SAT is an NP? Consider we have n input variables, x1 to xn, and we make the truth table for that, right? It's going to be true, 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 and then we do all those, and then it's going to be false, 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 right? This has size 2 to the n, right? So when we ask, is SAT NP, the reason is SAT an NP? The reason it's an NP is because we're asking, does this CNF have is there a satisfying assignment to the CNF corresponds to, in this truth table of size 2 to the n, does there exist a row that has a t, right? If this t exists, then we say the formula is satisfying. And the witness simply tells us which row to go to. It says that's the row. That's really what the witness is, right? Now, if we ask about SAT complement, what is the complement of SAT in natural language?
Not phi.
Almost. We still want it to be in CNF. Yes.
It would be if the CNF has no satisfying assignment.
Correct. So if a problem's in SAT complement, consider the same truth table, but instead these are all false. If there is no t, they are all f, right? So the question is, a formula is unsatisfiable if and only if its truth table is full of all f's. Can you efficiently convince someone that a formula is unsatisfiable? No. Like, you can't prove it, but that appears to be the case. So, and these are not formal proofs because we can't prove this. And if you could prove this, you would win $1 million. But there appear to be things that are that can be easily verified, but the complement problem cannot be easily verified. You can easily convince someone if a solution exists. You cannot easily convince someone that a solution does not exist, right? If you were to try to give them the whole truth table and say, here's the thing, the truth table is of size 2 to the n. The witness must be verifiable in polynomial time. It must be of polynomial size. So you cannot efficiently verify this in polynomial time. You can exponentially verify it. That doesn't make any sense. Just solve it. So like you can't quickly convince someone that a problem is not satisfiable, but you can quickly convince someone that a problem is satisfiable. There's an imbalance there. It's not very dual, right? Questions on SAT so far? Yes?
Is it faster maybe to compute that instead of a product of sums, using like a sum of products, because you just find the one that's...
It is known that DNF and CNF have different runtime. DNF is an order of ands, and I think you can efficiently compute DNF. And the tricky part about all NP-complete problems is they contain variants that are actually efficient, right? We'll come back to that in a second. Okay? Forget the fact that we have not shown that SAT is NP hard. We'll prove SAT is NP hard, right? But I want to argue about a variant of SAT called 3-SAT. Three-SAT is the same thing as SAT, where you have these formulas, and phi is satisfiable, and each clause has, at most, 3 literals. Okay? So the length of a clause may not exceed length 3, right? I claim two things. First off, I claim that 3-sat is in NP. Why? Yeah, same verifier. Don't make me write it down. Plug and chug, variables, okay, yeah, good, fine, okay. Now, next, I also claim that there is a polytime reduction from sat to 3-sat. So in some sense, the word reduction is meant to mean you're looking at a simpler problem. You're reducing the problem. It's smaller, it's more basic, it's simple. That's not always true, because sometimes you reduce to a problem that sounds more complex. So don't get confused by the word reduction. But note that what we're doing is simply a transformation from sat to 3-sat. Why are we going to do this? First off, let me tell you something we'll talk about later. The Cook-Levin theorem states for us that for all A in NP, there's a polytime reduction from A to sat. We also know polytime reduction is transitive. We know that A to B and B to C implies A to C. So in order to prove a problem NP-complete, you don't have to do this for all nonsense, because they did it for us. To prove NP-hardness, just go from sat to your problem. Let's go 3-sat. Why? Because you can already go from A to sat by Cook-Levin. So you go A to sat, and then you go sat to 3-sat. That gives you for all A and NP that you can go to 3-sat. So you go to 3-sat by just coming from sat. So you don't have to reduce from every problem, you just have to reduce from one problem. So we will give the reduction, and most of the times they will come from sat or other problems you've proven. And you only don't have to do, to prove a problem NP hard, you don't have to do it from all of NP. You just get to use Cook-Levin for free and just do it from sat. So we want to prove this refinement of sat is still as hard as sat. It's not any easier. Okay? So how are we going to do this? We prove it's in NP, we want to prove it's NP hard. If phi is in sat, we want to prove that f of phi for some function is in 3-sat. Right? In fact, if and only if. Now we just mentioned we cannot decide sat efficiently, but we can in fact translate sat efficiently. So what we're going to do is translate from sat to 3-sat faster than we can actually solve either of them, in fact. Right? Here's the reduction. Let a clause be x1 or x2 or xk for k exceeds 4. We will convert each clause of phi into another clause, f of phi, that is in 3C and F, but we will still maintain the correctness property in such that this is satisfiable if and only if this is. Now it doesn't say the solution has to be the same. It just says it has to be solvable if and only if this is solvable. There exists an assignment if there exists an assignment. The assignment could be different, but there exists an assignment. So what we're going to do is take each clause that's too long, maybe this is length 7, and we're going to break it down into smaller clauses, multiple clauses of smaller length. We can do that a polynomial number of times, and we will have reduced our formula into one that is at most length 3. So here's what we're going to do. If this is our clause in phi, we will construct clauses of the form x1 to x, double check, or k minus 2, or we add in a dummy variable z, and we break that with a dummy variable z naught, or z k minus 1, or zk. Okay. So we do this a polynomial number of times, and we've converted a long clause into two shorter ones. What's the length of this clause? Yeah, k minus 1, where these could be negated or something, right? This is 3. So we broke a length k clause into a k minus 1 and 3. Recursively apply this, that's what the reduction will do. So now we need to argue about correctness, right? So this is not really about like algorithms, but it's more about 2050 can you construct a proof. We want to prove this if and only if to be true. So we do any way we can do the. Do you guys recall how to do P implies Q? If and only if Q, you can break this down in two ways. You can do P implies Q, and then Q implies P, or you could do a P implies Q, and not P implies not Q, right? Both of those are equivalent to show an if and only if, and depending on one may be easier than the other. Let's do the second way. So we want to let phi be in SAT, and we want to prove that f of phi is in 3-SAT, where f of phi is the output of the reduction. The reduction takes as input a CNF, does not solve it, and outputs a different CNF with the correctness property. Okay? If phi is in SAT, what do you know about it? Yeah.
It must have a satisfying assignment.
There is some satisfying assignment. Okay, if that's true, what do you know about each clause? It's an and of many clauses, right? So each clause, a formula is satisfiable if and only if each clause is satisfied, right? So every clause has to have one light on. So each clause has at least one literal true. So for this specific reduction, we know one of x1 to xk must be true. And again, they're negations of things, right? So they could be negated. They're literals. But if one of x1 to xk is true, I claim that these two clauses are also satisfied. Why? What role does this dummy variable have for us? Sure, yeah.
Essentially allows us to pick which one we want to actually test with our x variables.
If it is in x1 to x k minus 2, then this with z not equaling 1 is a satisfying assignment. Of f of phi, right? So, but if it's not, if it is xk minus 1 or xk, then this with z equals 1 is a satisfying assignment. Of f of phi. So if phi has a satisfying assignment, then f of phi has a satisfying assignment. Notice we don't actually know if phi has a satisfying assignment. It could be unsatisfiable, but we've preserved correctness through this hat trick with the z. If one of these is on, then it's over here, flip this on, or if it's over here, flip this on, right? That'll be a satisfying assignment, so we see that we have a satisfying assignment, and we've proven that if phi is satisfiable, then so is f of phi. We need to do the reverse. If phi is not satisfiable, f of phi is not satisfiable. If phi is not satisfiable, what do we know about all satisfying assignments to phi? If phi is unsatisfiable, all assignments are unsatisfying for each some clause is always false. Some clause is always false. Let it be this clause. So none of x1 to xk are true. If that's the case, what does that tell us about the satisfying assignments of f of phi? There is no, if none of these are zeroed, if these are all zeroed for some clause, we can actually just plug and chug and get the same thing here. If we simplify that, what are we going to get down to? What is x or 0?
X.
Yeah. So plug in 0 for these. What are you going to be left over with?
Z and not Z.
That's part of f of I. So we see that f of I is unsatisfiable. Done. Oop. Thank you. So we see that we've computed a polynomial time reduction from sat to 3 sat. It's necessary that we do both parts of the if and only if to prove this, right? It's easy to make a mistake and have a reduction accidentally work out one way, but you need to prove the if and only if for both ways. Are there any questions on this reduction? Okay, now why 3 sat? Why not 2 sat?
We did 2 sat.
Yeah, I gave you 2 sat on the homework. Can you figure out a way? What do you know about 2 sat? What was the runtime of the algorithm I asked you to give to 2 sat?
Something polynomial.
Yeah, so you knew that 2 sat was in P. 2 sat is in P. Every 2 clause can be turned into an implication, which is a directional arrow in a graph. And then you just do a bit of graph traversal, maybe slow, but it's still polynomial. 2 sat is in P. But 3 sat is NP-complete. So if 3 sat is NP-complete, but 2 sat is in P, what does that tell you about your ability to improve this proof? We were only able to reduce clauses of size k to clauses of size k minus 1 and 3. Could we improve this to clauses of size 2? So does there exist a reduction from, let's say, 3 sat to 2 sat? Yeah, sure. I mean, like, this is not the only construction, right? You could imagine, for all possible diverse ways, what are the consequences of there being a way to reduce this to that? Now, this construction does not appear to immediately work for 2 sat, though, right? Because, why? Yeah.
Because when you do that, if you only split off one variable, your left clause ends up being the same size as the original, so it doesn't actually ever complete.
Exactly. You just add a bunch of dummy 2 clauses, but none of them get shorter. So this doesn't immediately work for 3 sat, but 3 sat to 2 sat, but can you improve it? If we know, suppose there's a reduction from 3 sat to 2 sat. We also know that 2 sat is in P. We proved something about polynomial time reductions. What is the immediate consequence of those 2 things? 3 sat would be in P. Okay? But we also know that for all A in NP, there's a polynomial time reduction from A to sat to 3 sat. Right? Which can then be reduced to 2 sat. So if A is reducible, if A is in NP, and A can be reduced to a problem in P, then we know about A.
It's in P.
So for all A in NP, A is in P. So 3 sat reduces to 2 sat implies P equals NP. So if you could improve this construction to just get rid of one more literal, you could win $1 million. The problem is incredibly difficult, but it has many simple, very simple avenues. So it's good bait for people on the internet to try to prove it, because it sounds like, oh, I found an easy way to do it. Just figure out a way to do this reduction. Finish the little last detail. It's as if there's a minus sign missing or something, right? It's very minor. But apparently this is a very difficult thing to do, and in fact impossible. Questions on that? Okay, let's do another problem. Let's call it circuit sat. Circuit SAT consists of encodings of circuits where there are n input wires, one output wire, and C, a Boolean circuit with n inputs, one output, and some input exists to make the output 1. Okay? Let's suppose, everyone knows what a Boolean circuit is. Let's suppose the circuit basis is also and, or, and not, as known. Okay? I claim circuit SAT is an NP. Why is circuit SAT an NP? You're given an encoding of a Boolean circuit, perhaps as a directed acyclic graph. The nodes are labeled as AND gates, OR gates, or NOT gates. And you were asked, there are n input wires and one output wire. You were asked, is there an input for every output? Is there an input you can set that makes the output bit 1? Yes?
Oh yeah, it's basically the same thing as what we did for proving that SAT is an NP. You just simulate the circuit with those inputs.
So what should we call them? Let's call them x1 to xn, maybe? And then we say, just plug and chug. Evaluate gate by gate. You can determine that if the output bit is a 1, right? How long does this take? Probably linear time in the size of the circuit. You just repeatedly apply the circuits. There's actually a lot of data structure efficiency stuff you can do here. I also claim that you can reduce from 3-SAT to circuit SAT. You can reduce, in fact, from SAT and not just 3-SAT, but we love 3-SAT because it simplifies every construction. You convert 3-SAT to circuit SAT, it's going to be simpler than converting SAT to circuit SAT. What is the reduction from, what is the polynomial time reduction from 3-SAT to circuit SAT? And again, we want phi to be in 3-SAT if and only if f of phi is in circuit SAT, where f of I is some circuit. So the input should be a CNF and the output will be some encoded circuit. What is the polytime reduction?
Oh, it's just you convert your thing into a circuit where the ORs are ORs and the ANDs are AND.
Perfect, that's all I wanted to hear. So n input bits, x1, let's draw it like this. Everyone know how to read a circuit, right? Okay, we'll talk. Well, let me draw it out a little bit first, and then we'll talk about it. That's a NOT gate, pizza. Those are OR gates. Space invader. And then the jellyfish is the AND gate. So what you do is, for each input variable, you add a NOT, it or NOT gate for each input variable. That's going to correspond to, if there's a satisfying assignment to it, you just put this will have the negation of that variable or the variable. Then for each clause, you create 2 OR gates, and then you just wire them up correctly however they may happen to go, right? You wire those up correctly for each clause, and in fact, if a variable is used multiple times, which is possible, then these just are allowed to, you fan out as unbounded, right? And then at the end, you just AND all your clauses. These are called gadgets, by the way. You construct a, for a clause or for a variable or for something like this, you construct a combinatorial object. A gadget is a technical term. It's a doohickey in which it simulates part of the thing for you in some way, right? We're going to prove many things are NP-complete require construction in the language of that object. For example, we'll be able to prove Mario is NP-complete. So we'll need like a sub-level of a Mario level that handles the clause part for us, or handles the ANDing or the ORing and so on, right? There are origami problems that are NP-complete, so you need parts to handle the ANDs and the ORs, etc., right? Permutation stuff. You need to be able to express it this way. So this is how we can, given a CNF, you can construct a circuit for it, right? This is the proof that circuit stat is NP-complete. How long does it take to construct such a circuit? Give me the actual power. Don't just say polynomial. Let's see if we can get this one. It's good, a good ability to upper bound something.
N log n.
Why?
Because you have, your first layer will have n gates, or like 2n little streams.
Okay, that's 2n.
And then each layer has half as many as the previous layer, because every layer sends like, this many gates, and they send 2 to 1.
But this could be at most n.
Yes.
So that's n,
Yeah.
and then that's at most n. N, 3.
Oh, right, because it's 3 sat. I was thinking like.
Now what would be the difference between sat and 3 sat here? This would be k little things, right? So by using 3 sat, the reduction is simpler. Okay. So this is the proof. Pretend everything I said out loud I would write down. But this is the obvious. I'm not even going to do the if and only if because the reduction is obvious. But we'll do more reductions in the future. Are there any questions on why circuit stat is NP-complete? Okay, I have one more thing I can show you real quick. Oh, that's not it. Let's do mean to stop. So this is the CLRS book, which is an algorithms book. You can see it's 1,300 pages. Let's see if we can find. There's a diagram in here I want to describe for you. Okay. So why is the Cook-Levin theorem? Hold on. Let me just do. Oh, let me do main desktop. Let's do extended desktop. Do this. Nope. Where'd I go? Oh, sorry. And then we'll do. So the Cook-Levin theorem asserts that for all A in NP, there's a polynomial time reduction from A to SAT, in the sense that SAT is a universal problem for NP. Now this is kind of difficult to prove, but it's very important. And this is called Cook-Levin, named after 2 guys, Steve Cook and Leonard Levin. He was working independently in the Soviet Union, and he proved the same thing. And basically, NP is a class of many, many problems. There's many things you can do in NP. Yet, SAT is a single problem. So how can an entire class of problems be reduced to a single problem? That's what the Cook-Levin theorem states. And all it really is a lot of Boolean programming. So we don't look at the Cook-Levin theorem. Actually, in 4510, we spend like 50 minutes trying to prove the Cook-Levin theorem. It's incredibly intricate, incredibly complicated. But, so most books don't actually bother to prove the thing because it's incredibly detail-oriented. So this is an algorithms book that gives like a high-level explanation about what Cook-Levin is. And essentially, what do you know about a problem in NP? What is the only thing you know about a problem if it's an NP? Yeah, if it's an NP, there's a polynomial time verifier. What can you do with this verifier? Nothing. You can run it, and then what? So what you actually do is you do, you can convert the NP machine into a polynomial size circuit. So we see here, let each C0, C1, C2 be snapshots of the machine. When you go to VMware and you click pause, it records all the registers, the RAM, the current pointers, whatever. Let all that be encoded into a string. And so C0, C1, C2, all the way to CT event are intermediate computation steps. And then between each one, you can construct a Boolean circuit, and here it's called M, where M is just some combination of AND, ORs, and NOT gates, such that it has one job. It takes on CI and outputs CI plus 1. So convince yourself, you're given a snapshot of the machine. Can you construct a Boolean circuit that will output the very next snapshot of the machine after a single instruction? That sounds plausible. Okay? We don't need to do the AND and OR NOT programming because it sounds right. Now let's say it was a move instruction or a jump instruction. You could probably figure out how that's actually going to work. You do some Boolean circuits. You have a generic M. Okay? What is the depth of this circuit? Each row of the circuit corresponds to a time step. The depth is in fact the time times m, which is a constant depth circuit. So it's in fact just the depth is the time. Okay? What is the width of the circuit? This is a harder question, in fact. How wide is a stripe of the circuit? It's as wide as the space used. Let's say the verifier needs cubic space to determine something. Then each of these could be bounded at most by a cubic of n, right? So the width is in fact the space. And then you have your single output bit here as a 1. So what you do is you convert the verifier into a circuit. You circuitify it, and you have a circuit sat, and not necessarily sat, but circuit sat is NP-complete without having to do a reduction from any known NP-complete problem. So we are thankful to Cook and Levin for figuring this out for us so we can just reduce from sat over and over. We don't have to reduce from NP because you would have to do an argument like this. Now, is this circuit satisfiable? Only if the verifier had an input that would make it accept. If there was an input to the verifier that would allow it to return true, then there was a sequence of input bits to this machine that would allow it to return true to this circuit. So in fact, there's an easier argument that circuit sat is a genesis NP-complete problem in the sense that everything reduces from circuit sat. And then you can reduce from circuit sat to sat, and then sat to 3-sat. So to go from circuit sat to sat, you have to do a kind of a flattening argument. It's possible, but it's a little cumbersome. We did 3-sat to circuit sat, but they're all end up being the same. You could make a similar argument for a 3CNF, right? So this is the reason that we are allowed to assume that sat is NP-complete. It is a genesis problem. So we don't have to reduce from NP each time. We can just reduce from sat over and over. And all of our reductions will come from sat or other problems we've proven to be NP-complete. For example, we proved 3-sat from sat, but then we proved circuit sat from 3-sat, and so on. We're allowed to chain things up like that, and it's going to make all our reductions much easier. So this is just a high-level argument about the Cook-Levin theorem, right? You believe you can construct a polynomial size circuit. Why is that circuit polynomial? It's important that the circuit is polynomial size as well, because it takes polynomial time to write it down. It's polynomial size because it's got polynomial depth, polynomial width. Polynomial times polynomial is a polynomial. Done. QED. Questions? All right, goodbye.